to also grade you as fast as I can, because eventually I need to give you all your grades before the final exam if possible, right? I think it is possible because we have like 2 weeks off between lab 10 and the final exam. The final exam is going to be on the last week, probably a Saturday. Do you mind? How about we talk about this a bit? So if I'm talking, May 10 is the last day, if I'm not wrong. The last Saturday would be May 8th. How about we have our lab on May 8th? You want that? Final exam on May 8th. Let me know. Yes or not? Final exam on Saturday, May 8th. Okay, so Roy has a chemistry exam. Is it chemistry or chemistry lab? Chemistry exam and another exam for someone else. Okay. Taba, how about, do you want Monday evening? Hello, Genti. Would you want Monday evening? It's gonna be Monday 10. Oh, that's the last day. I don't want to risk it. How about Thursday before the Saturday? So how about Thursday the 6th? Yes, Genti, I hear you. I think Thursday makes sense. And I'm gonna pick the earliest time possible. I don't know, 5? Okay. How about Friday? Friday the 7th. Remember, physics lab is not one of the toughest courses we're talking about. You do your lab reports, you're ready basically. Friday is good. So Jad said Friday is good. Okay. How about the timing? If we say Friday at 5, does it work? Or Friday at 6? I don't want it too late because some of you may have Ramadan as well. And not too early because probably you have courses, classes. So 5 and 6 are both okay. We can talk about this later. Okay, so this is tentative and I'm gonna keep it here. I would love to give it a shape. Yeah, so I'm gonna keep it here just in case. All right, we have next week to talk about it. Yes, no more than 1 hour. Last time I gave you 40 minutes probably. So I think I'm gonna give you the same length of the exam, but over 60 minutes. I want you comfortable because last time you were not comfortable and you didn't have enough time. Okay, so probably it's gonna be exactly like the midterm, but 1 hour long, push it 60 minutes. You finish earlier, you can leave obviously, but let me give you more time. Okay, but I promise we're gonna talk about this later. Any questions related to lab 7 and 8 before we start lab 9? Please let me know and please unmute to talk. I would love to hear you. Even if it's crowded at your place, look at the crowd in here. All right, so yeah, any questions related to lab 8 or 7? Or shall I assume your silence to be a negative answer? All right, we're gonna start with lab 9. It's gonna be quick, interference and diffraction. You see the outline is tiny. We're gonna discuss diffraction, then interference, then the experiment, and eventually the lab report. And while doing the presentation few hours ago, I just did it straightforward. But before we start, I really need to know, did you cover this in the course? Because it would change definitely my approach to the subject. Yes, I need to know if you did that in the course. You guys, I need you to talk to me. Okay, you did it already in the course, Jad, right? Okay, awesome. Yeah. Okay, Roy, why you're not taking the course? Did you take it already? Is that the reason? I need to know. Okay, so can I assume you already did something similar and on a different campus? When was that, in the fall or previously? And what was the course? Roy, unmute yourself and talk. Oh my God, 2 years ago.
Hello.
Really
yes, it was 2 years ago. I was at Lebanese University.
Okay.
It was a modern physics course, just like the one they give at LAU.
Okay.
So basically, it's everything optic, electric, magnetic.
Yeah, which campus do you go to?
I used to be at Fanar.
Okay, I was there in my undergraduate, you know. Are you talking about year 2?
No, first year.
First year. Okay. How are you finding the lab? Isn't it tough on you?
No, it's fine.
Okay,
Everything's
you're
good.
managing. Okay, I need to know. Roy, if you need help, let me know, okay?
Okay.
What about Karine? I just heard from you that you're not taking the course right now, right? So when did you take it? And where? Okay. Last year. Okay. ESG. All right. So I think your case is very similar to Roy eventually. Anyway, and how are you finding the lab? I know you're enjoying the lab. All right, good. And for the other ones, I assume that you're taking the course right now and you started diffraction and interference. Anyway, diffraction and interference that I'm gonna discuss now is something that you should cover in high school. All right. So it's not something really out of the blue. So it's simply how to describe it and how to the analytic the what can I say, the equation you need to know, and that's it. Okay. Well, I'm going to start with diffraction. You tell me what it is, when does it happen, why does it happen, what is diffraction? Yes, I'm all ears. Anything you can remember from diffraction. Diffraction for me is using one slit. I'm talking about one slit, not two slits. Anything you remember. Diffraction. Anything, even if it's wrong. I'm waiting for your answers. Come on, anything you remember. Diffraction. I'm talking about diffraction of light, obviously. Why does it happen? It's due to what? How can you describe diffraction? What do you see when diffraction happens? In which cases diffraction does not happen? Do I have diffraction of other waves too, or is it only light? Can you please answer me? You can simply say, I know nothing. Okay. So anything, Yara, about diffraction? People, different n. Okay, I'm gonna write different n. Maybe it happens when we have slits. So when light goes through a slit, probably. What else? Bright dark fringes. So Hussein remembers that we can see bright and dark fringes. Okay, do you remember, can you describe them, the bright and dark fringes? How do they look like? Other waves do undergo diffraction, for example, sound waves or water waves. Water waves do undergo diffraction. Yeah. Okay, what else? Anything you remember about the bright and dark fringes? For example, how they look like. Alternating. Okay, this is interesting. So we have alternating bright and dark fringes. Anything you remember about the intensity, bright and dark fringes, or the size? The light going in one direction goes in a different direction. Yes, so change in direction of light, change in the direction of light, or isn't that diffraction of light? Or isn't this diffraction? Yes, Guy, yes, they told me. That's good. Did you do well? That's great. Okay, let me just move those away. All right, anyway, what is diffraction? Diffraction happens, and we can let me start by describing it, and then I'm gonna discuss how why it happens. So this is a certain wavelength. It could be a water wave, and you're looking from above. So those are wave. I'm losing my words today. Anyway, the wavelengths is the difference between the two peaks, and these are wavefronts. That's the word. So wavefronts, you see them parallel, and then due to a certain aperture or opening, you can see a slight change in the motion of the wave, and you can see a bit that the wave is diffracting a bit. Wavefronts, yes. And here you can see that the same thing happens, but something else would happen. Can you compare both cases? And can you say why they're different? So what's the difference between the two cases? Yes, and what happens? So in this case, Yara is saying the slit is smaller than the slit I have in here. Slit is basically any opening. And as a consequence, Yara is saying we have some diffraction in here, and I have more diffraction in here. Okay? Yeah. This is another case. I think this is water in a container, a very shallow container, and and it's a transparent container, and you have a light bulb under the water, so you can see it very nicely. Also, you have something here like a ruler that looks like this. This ruler is attached to a motor, so the ruler will go up and down on the surface of water, creating vibrations. You can see plane wave fronts going into the slit, and you can see some diffraction happening. Here, the slit is bigger in size, and diffraction is barely visible. You see, those lines are practically parallel. So it is as if diffraction did not happen. It's really, really light. Who can discuss this? What do you understand by this one? What is this plot? What does it show?
Doctor, before going to the plot, could you please repeat the two figures, the difference between those?
Yeah, did you understand the difference between those to start with, Roy?
Yes.
Okay, this is exactly the same. I have a small opening, I have a bigger opening. Water waves coming in, you have diffraction. You see the diffraction. By the way, if you want to draw the light ray or the ray or whatever you want to call it, it has to be perpendicular to the wave fronts. So this is how the ray is going. I'm not talking about light ray though. And this is how the ray is going. And you can see that, so this is the direction of propagation of the wave. You can see here that diffraction is very light, and here diffraction is like more pronounced, like I have more diffraction. So according to Yara, and I agree with this, and probably we can write it in here, the smaller the slit, okay, or the narrower the slit, the more diffraction I have. Okay? Probably this figure did not make sense to you. Now, does it make sense? Roy? All right.
Yes, it does.
All right. So I was a bit, I love this experiment. It's so pretty, isn't it gorgeous? I was explaining how we had a container, transparent and light underneath. You can do this at home. صينية رفيعة تكون transparent, or like a plate, and you shine light under it, and you can have a ruler. You don't need a motor. Just put the ruler in the water and put the ruler up and down to create waves, and you can shine light under it. It's really nice. Or if you want, you can shine light above it and see a nice picture on the floor if your floor is homogeneous in color. It's nice. I love it. That's why I was talking about it, and probably I confused you. Now let's look at this graph. What does it show? I'm only dealing now with description. I'm describing. That's it. Can you describe the graph? What is that? What does it show? Yes, anything. I versus theta. Chinese to me. What's I? What's theta? Let me start with what's I. intensity of light, basically, not the wave. This is light, to help you a bit. So, and to be honest, this is the screen where the diffraction is happening. And you can see at the center of the screen, you have a spot that is very intense. It's a lot of light happening at the center of the screen. And then you have less light and less light. And probably, according to Hussein, I can call this a bright fringe. And this is another bright fringe of very light intensity. And I can call this a dark fringe. So this is a dark fringe, and this is another dark fringe because the intensity is zero. Intensity zero means no brightness, so dark fringe. And I'm gonna call this a bright fringe, even though it's tiny in intensity. How many bright fringes can you count? Can you tell me? How many bright fringes can you count? 3. So if I use this highlighter, we have the central one, we have this one, so 2, 3, and probably you have a tiny one in here and a tiny one in here. You can count it if you want, Roy, okay? You can simply ignore it and say it's not fully shown. All right, so what is the angular width? The angular width is basically as you go away from the center, but it's not in linear centimeter, it's an angular width, you know, but we can simply say distance away from the center and call it distance. All right, so now let's start with a good definition of diffraction. I will definitely not read it. I will say diffraction is the spreading out of waves. So I'm gonna underline aperture. Also around any object, like if you have a very sharp object, it could be a mountain or it could be a very sharp hair, and you shine light in this direction, diffraction is going to happen a bit at the top of the mountain or around the hair, you know. Anyway, it could be an aperture, okay? Now we're going to discuss the size of the aperture, same order of magnitude of the wavelength. In this case, diffraction occurs, but it's very light. For very small aperture, I will have, okay, they're talking about obstacles. Anyway, here you can see again the wavefronts that are planes, and you have some diffraction happening. You can see the aperture of a very small size. Here you have the same thing happening. Here the aperture is so much bigger, and you can see that basically diffraction is not visible at all, okay? Fine. Now a bit about how things would look like and which equations to follow. Again, this is where I'm shining light. This is an obstacle, and you can see a small aperture. The distance between the slit and the screen is called D, and you can see it in here. This is the screen. It could be any white paper. Basically, if you look here, this is the slit. It's really big because it's a zoomed in picture. Let me call the size of the slit A. I'm gonna fix this and call it A just to follow the lab report, okay? You can see that this point will act like a source of light, and it's gonna send light in one direction. All the points of the slit are gonna act like sources of light, and they're gonna send light to in the direction of the screen. So if I need to compare A1 and B1, and that's simply an example, you can see that there is a path difference between the two lights traveling in a certain direction to the screen. And this is basically an approximation. And the path difference could be visualized by this triangle, you know? And if you really think about it, the path difference that is this is equal to A sine theta, okay? However, I would think of this triangle and I would think about A being this. So I would say A over 2, unless you want to compare A1 and B5. All right, anyway, all this is an approximation because we're trying to assume many things. Like, for example, this could not be a perpendicular if I'm talking about different positions in the slit, but this is only an approximation. Fine, there's no triangle that would show you exactly that the path difference is this. Unlike interference, where you have two slits and you can directly and see the path difference between slit 1 and slit 2 and measure it very well. Here it's a bit different, and this is an approximation only, okay? So if I assume that the path difference is related to A, which is the slit width, and to theta, what is theta? To be honest, theta is this angle, and at the same time it's this angle, because you can see that this line is perpendicular to this line and this line is perpendicular to the line to the screen. This is the real theta I'm talking about, okay? So theta is, you can call it the angular position of any point on the screen. So if I take this point, theta is the angular position of point P, okay? So I can say that the path difference is a sine theta. Also, I can say to find sine theta itself, I can approximate sine theta by tangent theta, because we're talking about very small angles. Why very small angles? Because usually D is very far, like the screen is very far, and I'm talking about D that is beyond half a meter. I can simply replace sine theta by tangent theta, okay? So I will replace all of the sine theta, all this, by y over d. And what is y over d? Y is how far away point P is from the center, and d is this one. So tangent is opposite over adjacent. That's why I have the right to say tangent theta is y over d. Probably I'm confusing you. So the path difference, that is a sine theta, I can write it as a tangent theta, or as a times y over d. Now for me to have a bright fringe, the rays should have a path difference equal to an integer multiple of lambda. So m is an integer and lambda is the wavelength. So when I have m lambda, it means I have a bright fringe. So this equation would work only for bright fringes, okay? Again, what is y? Y is the position of the first bright fringe. Again, the bright fringe, this one, just a second, there's something wrong, and this equation is a big approximation. Okay, so m equals 1 is the position of the first dark fringe, and this is order 1, this is order 2. And dark fringe happens not for this one. Yeah, no, I just did a big mess. All right, how about keep this for a while, and I will find something to simplify it for you. Okay, I'm not gonna use this one, I'm gonna use something else. Fine, so I'm gonna go back to this slide in a while. So far, this is what you have in the lab report to follow. And even if I follow a different method, I will end up with this equation as well. The mess is not here, and the mess is not here. The mess is exactly how we define path difference, okay? So I need to come back to this with a good explanation. All right, anyway, now interference is basically much simpler. And I need, before we start the experiment, to add a slide before I forget to compare both. So probably for me not to forget, compare. So compare diffraction, and I mean by compare at least the description of what you can see, and interference. Okay, so I will get back to this after a moment. All right, so interference is basically you don't have a lot of estimation. You simply have to see a light ray going from this point, another light ray going from another point, from another slit, and they do actually meet. You find the path difference directly. Bright fringe is n lambda, dark fringe is an integer of lambda over 2, if you want to call it, or odd lambda over 2, and you're gonna be okay. And this is a good picture to explain it well. So the path difference is d sine theta, and you see m equals 1 is this first order bright fringe, so no confusion in here. So probably if we fix the diagram, we're gonna be all right. So I'm gonna send you an appendix after the session. And m equals 2 is the second order bright fringe. M equals 0 is the zero order bright fringe, you can call it the central fringe. Same thing, I'm gonna replace sine theta with tangent theta, and the thing is gonna be exactly the same. So what is the difference between interference and diffraction? For diffraction, we're talking about an infinity of tiny sources. For interference, we're talking about two sources, okay? Before I move to the next slide, I need someone to describe those two diagrams. Let me start by describing the first one or the second one, and step number 2 would be to compare them. So you tell me. You tell me, how do you describe it? Other than the fact, Hussein, that you can see bright and dark fringes alternating. Yes? Okay, this is, you're comparing both. Are you sure they're larger? It's a good question. Think about it. Who is the, okay, taller? Yeah, probably. Thinner but longer. All right, so if I need to discuss the size of the fringe, I would discuss the width of the fringe. By the way, the width of the fringe, isn't it related to y? Because y is how far away you are from the central, right? And if I go back to the y equation, probably we can try to write the y equation. What is y equal to? Isn't it m lambda d over big D? Big D is, by the way, the distance between the slits. So let me say it again. M lambda D over small d. Am I right? Yeah. So it is somehow, so if you look at y and you look at lambda, they're proportional. Who has a bigger lambda? The red or the green? So which has a bigger? So green has a bigger lambda, green has a bigger frequency. So red has a bigger wavelength. Can we agree on this? Which means that red has bigger fringes. Yeah, can we say that? Do you agree? You can disagree with me. I do a lot of mistakes. Do you agree with me? And you can see red is a bit thicker than green. All right. Why do we have this looking a bit taller? I don't know. Probably it's not exactly the same setup. I don't know. Probably this is how they looked like. So probably it depends on the slit itself. If the slit, the slit is rectangular, probably it has to do with how long the slit is. I don't care about the long. I care about the width for the moment. All right, this is one thing. Tab, can you tell me now what's common between those two observations with two pictures? What's common, not what's different? Is that diffraction or interference, by the way? It's both. Thank you, Yara. Can you please explain? Okay, so Yara is saying we have two slits, so interference is happening. However, the slits are so small, so diffraction is happening on top of interference. Since you're talking very interesting stuff, probably we can discuss it in here. Can you tell me how to describe an interference pattern? Okay, how do you describe it? Other than the fact that we have alternating bright and dark fringes and dark fringes. What else do we have? Can we compare, yeah. So what's the difference between an interference pattern and a diffraction pattern? In an interference pattern, I have alternating bright and dark fringes. Also in the diffraction pattern. How do we describe the interference pattern other than the fact that we have alternating bright and dark fringes? Can I say that all the fringes have the same size? It is actually one thing that is very important that I'm going to show you again. And three, and this is also important, intensity of all the fringes is approximately the same. I'm going to say it's like ideally it's the same, but in the lab it's going to go down just a bit. I'm going to say approximately the same. Approximately the same. Okay? So now if I need to write down the diffraction pattern, how about I copy paste this one and change a bit in it, and probably you can guide me through it. So diffraction pattern, what's the difference? Diffraction pattern. Do I have alternating and bright fringes? Yes, we do. All fringes have the same size, right or wrong? This is what I want you to tell me. The intensity is not the same. Okay. The fringes, according to Roy, are not the same. So if we go back to the diffraction pattern, which is here, it's very important to know that the central fringe is double in size. Okay. So the central fringe is double and the other fringes are low. And I think we need a diagram to show you, and probably I can do this in a while. So I'm gonna say they don't have the same size. The central fringe is double in size, because this is the only way for you to recognize if your pattern is diffraction or interference. You need to know the difference. And for the intensity decreases a lot as you go away from the center. And you can see it in our intensity diagram in here. The central fringe is double in size. You see, from 0 to 0.005 times 2, and this one is only half the central fringe. You can also see that the intensity was 100% and then basically nothing. Okay, Jad, no problem. You can watch the recorded session later. So what I'm trying to show you here, that you can barely see the central fringe and 2 extra. If you go to the lab, this is what you can barely see. However, for interference, you can easily see up to 5, sometimes 10 different fringes. And you can see they're basically the same brightness and so on. Okay? This is very important. So this is interference. You can see this one is a dark spot because of an envelope I'm talking about. And the envelope is visible in your lab report. And how come I did not show it to you? I'm going to show it to you in a moment. All right, so again, what I have here is interference inside a diffraction envelope. This is a bit confusing. I will get back to it in a moment. So what you need to know before we leave interference, it's basically the same equation that you have for diffraction. However, small d is the distance between the slits, and the size of each slit is not taken into account to discuss the fringes. And for the diffraction, we're dealing with the same equation. However, we don't have small d, we have small a, and a represents the size of the fringes. I think this diagram will be okay if I simply move, and there's nothing wrong with the analysis. I can simply move m1, so this is the wrong thing. This is m1 equals 1, and this is m2 equals 2. And this is wrong. This is m1 equals 1, this is m2, m equals 2, and this is m equals 0. So nothing is wrong with this diagram. I know this is still an approximation, okay? It's only that the position of m1, m2, m3 were wrong. Also, I wanted to show you something before I leave this part of the presentation. The intensity decreases a lot, right? Here for the interference, in the ideal case, and let me pick black or something very dark, probably green. In the ideal case, the intensity has to be equal, but it will lower a bit, okay? And I don't want this to be confusing for you. For the interference, the intensity will decrease, but just a bit, okay? For diffraction, it's gonna decrease a lot and not a bit, and I think this is an excellent description. This is something done in the lab, so those values are experimental values, okay? What else? Now the experiment itself. Did I miss anything? Let me show you the envelope, not this one, this one. The envelope is very nice to see, and it is here. So here you have the diffraction envelope. So why do I have the diffraction envelope? Because the slits are very small. So I have an envelope of diffraction. And inside the envelope of diffraction, I have interference. And you will see in the video of the lab that you have up to 10 small fringes that are very nicely visible. They are very small, yes, but you can count them easily. And then you will see dark, and then they will repeat again. However, for the diffraction pattern, that is basically, if you want back to this one, the intensity curve, you can barely see 3 spots, and the central one is really big, okay? Roy is asking, are the dark fringes within the order of lambda over 2? Yes, You can simply say, Roy, for the dark fringes, instead of using the equation m lambda over 2, m lambda, you can use odd lambda over 2. So 1 lambda over 2, 3 lambda over 2, 5 lambda over 2, 7 lambda over 2, and so on. Or the odd value can be easily written as 2n plus 1 or 2n minus 1. Okay? So what I'm doing here is I'm only writing what's happening for the bright fringes. Okay? Okay. Now the experiment. The experiment is very simple, but I wanted you to see how the equipment look like. This is the laser source. You can simply turn it on and off, and this is what the lady is doing here. And the wavelength, the nominal wavelength is written on it. It's red laser light, like the one you can find at the $1 shop, but probably this is a better quality because it gives you a short spot. That's it. Okay, but it's the helium neon laser that everybody use. So we're not using green, only red. And you can see the whole thing is gonna be on an optical bench. So everything will be aligned and you can easily measure the distance between the screen and the slits. This is where the slits are, but this is, you can rotate it right and left to pick any slit you want. You have different sizes and different shapes. You have rectangular, squared, circles, uh, and as you can see, you have this one that would give you a single slits only, and this is double slits only. So you remove the first one and you put the second one for the second part of the experiment. The laser and the slits should be like touching each other, very close to each other, okay? And the distance between them is negligible. However, negligible would be for me around 3 centimeters because you can see the leg in here and the leg in here and the ruler. By the way, this is a regular ruler. You can measure the distance between them and it's not really zero, okay, because they're thick, around 2 or 3 centimeters. That is negligible because we're talking about laser beam, a cylindrical beam, so it's not gonna diffract or do anything. And then you start measuring the distance between the slits and the screen and call it D. This is a white screen. Usually we put a white paper on it and we limit with a pencil the location of the fringes, and then with a regular ruler we can do the measurements. Okay? Yes, the measurements. Yeah. This is something that we usually can see in the lab. Very similar. This is what you will see in the lab. Can you tell me if this is diffraction or interference? And why? So Yara is saying this is diffraction. However, Yara, you can see that the central fringe and all the fringes, they have the same size, or am I wrong? All the fringes, they have the same size. So is that interference or diffraction? It is basically interference. I always have diffraction. I cannot get rid of it. So this is interference. Interference. The tiny diffraction happening is due to the fact that the two slits are tiny. There's no way on earth you can have interference without this diffraction. So if you zoom in and you ignore what's happening, but we're not gonna do that, or if you simply crop the picture and focus on the, okay, what just happened? Okay, just a second. Okay, redo. Yeah. So if you try to ignore what's happening away from the center, just to reduce, I don't want to call these sources of errors. These are happening for a reason, you know, but we need to ignore them because we want to study interference only. And there's no way on earth I can have two slits that are not too tiny. So diffraction is going to happen on top of my interference. So the best way to know is to observe the sizes of the fringes. And how many fringes can you see? I can count easily 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and that's awesome. For diffraction, you can barely see 3. If you're lucky, you can see 5. And I think I owe you a picture for diffraction. A diffraction pattern, okay, how does it look like? And why not put it in our presentation? And I want a real one. This one, this is what you will see exactly in the lab, and I love it. And let me save the picture, save image as whatever, because I need to delete it later. So, and I'm gonna put it here in the next slide. Yes, and let me remove those and this. Yeah, and let's describe it. Are you ready to describe it? Oh, that's big and awesome. Probably move it to the side. Yeah, and probably we can discuss the width a bit. First of all, let's compare the central fringe to the other fringes. So is that interference or diffraction? So in this case, do I have interference or diffraction? I have diffraction, obviously, and the best way to tell is to look at the central fringe. This case and this case, we're talking about a very, the width, you see the width is big. Yeah, I think this is the width. I don't know what it represents, but we can tell. In this case, you can barely see two from the side and three from this side and the central one. For this case, you can barely see one from this side and one from this side. I don't know if you can see this one, and you can see the central one. So you cannot see a lot of fringes. If you're lucky, you can see four. In this case, it's really special because they're tiny in size, the fringes, and that's why you can see more. But like, look at interference. You can easily see beyond 10. And this is a random case. Sometimes you can see more than this, okay? So this is the difference. So the best way to tell if the pattern is one slit or two slits is by looking at the central fringe, if it's double or not. So again, here, all the fringes have the same size and you can measure it with a regular ruler. All right. How is it going so far? Because I'm not happy with the presentation. It's a bit confusing for you. It's my bad, but it's okay. It happens. So far, we have a relationship for diffraction. So what you need to know, diffraction, interference. Personally, I call them both diffraction with one slit, diffraction with two slits. You need to know the difference between them. If you are given a pattern, you need to understand which one is two slits, which one is one slit. This is one. Another thing, you need to know the relationship between the size of the fringe and the wavelength and so on. And now for the lab report, what you will be given. You will start with diffraction, and we will definitely mean by diffraction one slit. You will fix the distance to the screen to be a constant. You will be given the slit width, and we call this small a. Separation between two consecutive dark fringes will be measured for you, okay? This is not the position Y, it's the separation between two consecutive dark fringes. I will go now to the diffraction pattern again to show you which one I mean. So this one, separation between two dark fringes. So this or this. It could mean the size of one bright fringe. It could mean half the size of one central fringe, you know? And by the way, as you can see, we have many trials. I can take the central fringe divided by 2. I can take one bright fringe divided without dividing it by 2. I can take two consecutive bright fringes and divided it by 2. By the way, it's very difficult to see the position of the bright fringe. As you can see in here, or probably let me show you a diffraction pattern. You don't know where the bright fringe is. So some students would want to take the center to the center, but it's so much easier to take the center of the dark to the center of the dark. You see what I mean? That's why in the lab report they say the size between two dark fringes, because it's easier to measure. If I go back to the equation, how is Y related to the size of a fringe? You can simply replace M by 1. If you replace M by 1, you will take this distance, right? And this would mean what? It would mean one size divided and plus half. Think about it, okay? Yes, think about it. And again, back to the lab report. What they give you here is not Y. They give you the separation between two consecutive dark fringes. Now your job is to calculate from this value the wavelength. Here I have 1, 2, 3, 4 trials. That should be very close. We're doing so many trials because the measurements may not be precise. Again, I'm measuring the size of a fringe. I'm not doing it directly. I'm measuring many fringes, dividing it by their numbers, taking into account the central fringe to be like 2 fringes, just for me to increase the precision anyway. So you will find the wavelength for each. Then you will change the size of the slit, and you will find the wavelength. You will use the values given to you, and you will calculate the wavelength again. And the wavelength is going to be the same all over the table because we're talking about the same light, around 600 something nanometers. Eventually you find the average and the RMS. Okay, and you compare to the expected value. The expected value is the one written on the laser source itself. I remember 630 nanometers, but I will confirm with the table of results. And then they ask you what happens, how is it increase or decrease when the slit is increased. Talk a bit about the relationship. Use your data to discuss the relationship because you have a lot of data in this table. If you want to say proportional, try to find a constant ratio. If it's inversely proportional, try to find a constant product, and so on. This is a conceptual question that you can answer on your own. For the next part of the lab report, you are given the interference, or what we call diffraction with two slits. But here you have to be careful. You are given the distance between the slits, small d, and A, the size of each slit. And you know for a fact that the size does not affect the separation between the dark fringes. It only affects the bigger envelope because A, the size of one slit, will affect the diffraction envelope and not the interference itself. As you go back to the equation of interference, you see D and not A. And D is the distance between the slits. So it has nothing to do, it's not going to affect the position of your fringes and therefore the difference between the fringes or the separation between the fringes. As you can see, you have those two cases where D is the same but A is different. You have those two cases where A is the same and D is different. You see? And this will give you some room to analyze your values, and they will tell you how this will affect this and so on. So probably you can talk about the diffraction envelope and the interference pattern. This is average and RMS, and this is talking about white light in general. Um, what would you see on the screen if you replace the laser with an incandescent lamp? So which is a bulb, a regular bulb. In this case, you have to think laser versus bulb, white light versus one micro, what would you call it? I'm losing monochromatic light, right? So monochromatic light versus white light, which is a polychromatic light. Laser beam, which is coherent versus a lamp, a bulb. Think about it, and probably you can discuss the fact if interference would happen. And this is under interference, so under two slits. And if you believe interference would happen, can you describe the interference pattern, yes or no? So you can read a bit and you can think about it, and you will let me know if you have any problems. And that's it. So I know for a fact that for the diffraction, we fixed a bit the drawing. I'm still not very happy with the mess. I'm gonna send you an appendix with an explanation because I really, yeah, monochromatic. Thank you, Roy. I really care about this to be very clear. And even if you don't really need it for the experiment, clear would help you for anything later on. So it would be a tiny appendix. If needed, it will be a recorded section of a minute or two where I explain it, but I think I can easily explain it with some notations, okay? So yeah, I'm not happy with it. I know for a fact it's in the lab report, so why not fix it from the lab report as well? Okay, because you can see. And I don't want to analyze things as a function of y. I would love to analyze it as a function of the separation as well, because I don't want to leave this for you to think about it. Yeah. So that's it. Any questions? You can go back to any slide you want. And meanwhile, I'm going to save this under your class so I can share it with you. Yes. All good. All right. So the lab report is not difficult, but it's very important for me for you to be able to describe the difference between the two, because this is what matters, and this is why we give both in one lab, because we need you to see the difference and we want you to enjoy the difference between them. And yeah, and eventually the calculations are no big deal. Yeah. So that's it. I'm gonna stop sharing, probably start by stop recording this session.